Banker's algorithm is designed to decide if a state is unsafe when using multiple instances of resources. Each process must tell you before it begins exactly what resources and the number that it plans. It could be its maximum allocation or maximum request. When a process requests a resource, it may have to wait if allocating that resource causes it to go into an unsafe state. And when a process finishes, all of its resources must be returned within a finite amount of time. So Baker's algorithm is one of those that is going to absolutely show up on your quiz. And it's also one of those processes, much like CPU scheduling, where the way that you break the problem down and you write the problem down can be very helpful. So at a high level, you have 4 data structures. One is called available, max, allocation, and need. Available is a vector length of m, and m is the number of resource types, so you can figure you have pools of resources here. Max is a matrix is the number of processes times the number of resources. Allocation is also the number of processes times the number of resources, and the need is a matrix of the number of processes times the number of resources. So if you think about max in terms of you're going to have columns for each resource type, and then maybe rows that correspond to the different processes. Okay. Here is the algorithm for Banker's algorithm. You're going to have 2 additional vectors, work and finish. Work is the M and finish is the N. So you'll initialize the work is equal to available and finish is equal to false for every single process, and I is for the processes. Find an I such that both finish is false and need is less than work, and if no such process exists, go to number 4. If you get to number 4 and you've managed to mark true for all the processes, then the system is in a safe state. If you get to 4 and you cannot mark true for all the processes, then it is in an unsafe state. And step 3 is where you try to mark the processes as they have enough to finish. Work equals work plus allocation. Finish equals true, then go to step 2. And so you kind of loop between 2 and 3 until you can't do 3 anymore because there are no more processes, and you go to 4 and decide if you're in a safe state. So we probably want to work out some of these because it's a little easier to see how the process works when you work them out. All right, so here's part of the algorithm. We will actually talk through this in an example, so I'll come back to this slide. So here's an example of a system state, a snapshot at time 0. We have 5 processes, P0 through P4, and 3 resource types, A with 10 instances, B with 5 instances, and C with 7 instances. And so the allocation data set we talked about, and basically this is the number of resources currently allocated to each process. And of course the max column is what they have said is the maximum they will ever use. And available is what's left in the system. And if you look at the allocation, so if you look at A, we have 2, 3, which is 5, plus 2 is 7, plus 3 is 10, that's 10 instances. And in B, we have 1 here, 3 here, 5 instances, and the same with C. There are 5 and 2, and there's 7 instances. But of course, if we look across the maximum that one could allocate, they're certainly under the number of resources that are available, but obviously all of them cannot be allocated or fulfilled at the same time. So the question is this a safe state? So if we look at the safety algorithm, we're going to have work, which is available right here. Work equals available. And finish is false. So let's see. I suppose I could do something here. So all of these is false. Yeah, drawing on this is going to take some time, so I'm not sure that's going to be the way to go here. Interesting. False. Okay, so the whiteboard would be easier. False and false. Okay. Useless as the days are long, so we'll just move on. Find an I such that need is less than work, and well, the finish is false and need is less than work. So we don't have a need here, right? So we need another thing. And oh, geez, I wish I could type. Can I type on this? Typing would be a lot easier here. Nope, doesn't look like it. So we have a need box. And if you remember when we looked at the data sets, need was actually max allocation minus allocation. So a need is actually going to be this table minus this table. And so here for the first process, we've got P0 has 0 of A allocated but can use up to 7, so 7 here. And it has 1 of 5 allocated, so it could need 4 more. And this one has 3 max, but it doesn't have any allocated. And here we have, let's see, 3 minus 2, that's 1, and it doesn't have any of the others allocated. Okay, and then here we've got 6, and there's 0, and then 0, right? And we've got 2 minus 2 is 0, 2 minus 1 is 1, and this one is 1. And here this is 4, 3, and 1. Okay? So now the question is, if we go back and look at that step, is there a process where the need is less than what's available, or the work, right? Because available equals work. That's what we decided, or work equals available. Okay. So if we go through, obviously, we can't do 7A's because we don't have that available. We can do either P3 or we can do P1. But those are the only ones we can do. It doesn't matter which one we do. We can do either one of them. So if we want to do, let's say, P1, so we'll cross this out and make this true, right? And what happens is basically what we're saying is that at this point there's enough resources available for process 1 to get their maximum allocation and complete. And once P1 completes, the 2 A's that it's holding actually get added back to the pool, right? So now we've got 5 A's, 3 B's, and 2 C's, okay? And so now we'll start that all over again. Is there something here? And I think we know P3 will do it, so we'll cross out P3, and P3 will complete. We'll make P3 true. And we're going to add what it currently has allocated back into the bunch, because now we know it can get its full allocation, finish up, and let go of its resources, okay? So now it looks as if we can actually pick any of these to finish. It looks like this one will finish, this one will finish, and this one will finish. And you should actually go through all of the numbers and make sure that it works. But what will happen is we will actually be able to set all of these to true. So the system is, in fact, currently in a safe state. Okay? And we will notice that the system is in a safe state, and the sequence we could have used or did use, we started with P1, we did P3, then you could do P4, P2, and P0, and it does in fact satisfy the safety criteria. Okay, so now we have the system and we know the system's in a safe state, and now we would like to grant the request to P1, process 1 of 1A and 2Bs. Let's see. So we've got allocation and need, and we know, what do we know here? So we have to check, one, that the request can be granted because of what's available. And it can, because this is what was available on the last screen, right? And so, but once we grant that request, this is what we'll have left. So 3 minus 1 is 2, 3 minus 0 is 3, 2 minus 2 is 0. So this is what we would have left. And so this is kind of a hypothetical. We haven't granted it yet. We're just trying to see if we can grant it and the system stays in a safe state, right? So we go ahead and we take this out. And then, of course, P2, which before had the allocation of a, P1. P1 had the allocation before of 2, 0, 0. We're going to add the 1, 0, 2, which makes its allocation now 3, 0, 2. And now we want to be able to see, again, do the banker's algorithm to make sure that the system is indeed still in a safe state. And the system is, if it is indeed still in a safe state, then we can go ahead and grant that request. So we have 2, 3, 0. And need here is P1, so we can actually, So we can actually grant this allocation, and then we know that we'll get these back, right? That's the P3, and that'll be 4, 4, 1, okay? So that's P3. And then with 4, 4, 1, let's see, we can do P4 or P1. And it looks like they did the order of P1, P3, P4, P0, P2, which is much like what we did before, and I'm kind of going in a different order, obviously. I said P1, which would get us 3, 0, 2. That does not look like a 3, right? And then, of course, you can add those down, and you can go through each one of these and see that, in fact, yes, it does satisfy the safety requirements. And this is one sequence, although I had another one. So now the question is what if, okay, what if I wanted to grant this request, the request for 330 for P4? Well, first of all, I guess we can assume we're starting with this state of the system, that this P3 request has been granted. But if that's the case, you can't actually grant it because you don't even have enough of the A resource available for it to be granted. So obviously, that can't happen. However, if we wanted to look at this request by P0, 0 to 0, if we did that, 0, I keep turning on my pen. So we're going to take 2 here, and that's going to leave us with 2, 1, and 0. And that's going to change this to being 0, 3, 0, right? And then we're going to take the 2 off of the need here because that's going to be 2, right? So now we just go through and do the same steps. Are there any of these that can actually do the 2, 0, 1? And actually there isn't. None of it. You need 7 A's, 6 A's, 4 A's, and then here You can do 1 here, but we don't have the C's available for this one. So this actually does leave it in an unsafe state. You are unable to actually take all of the, get enough resources to make sure that all the processes can be finished. So we would not grant this request for the 020. So we'd say no here as well. No here, and no here. Okay. These are examples that are in the book. Please walk through them. Make sure you're familiar with Banker's algorithm, because this will absolutely be on the quiz on Tuesday. So that was deadlock avoidance. So we're going to avoid a deadlock. In avoiding a deadlock, this means that it's not that we know whether a deadlock is going to happen or is not going to happen. We just know that it can happen. So we'll try to keep out of states that allow deadlocks to happen. There's also deadlock detection. You could allow the system to enter a deadlock state, but then you'd need to not only detect the algorithm, but you'd have to figure out how to recover from the deadlock once you've detected it. Again, we're going to divide the systems into 2 kinds, one where there's a single instance of each resource type, and one where there are multiple instances of each resource type. So if we're considering systems where there's only one instance of each resource type, we can actually maintain a graph that tells us who is waiting for, which process is waiting for which processes are waiting for resources held by other processes. And periodically you can invoke an algorithm that searches for a cycle in the graph. If there's a cycle, then there's a deadlock. The algorithm to detect a cycle in a graph requires an order of n squared operations, where n is the number of vertices in the graph. So here's an example. We have a resource allocation graph and the corresponding wait for graph. Here we can see that the resource allocation graph actually has both the resources and the processes. And in the corresponding wait for graph, we actually remove or reduce the resources and just use the processes in the graph. And so here we can see that there is a cycle right here. As P2 is waiting for something held by P5, and P2 is waiting for something held by P3. We can see that there is actually a cycle here. If we have several instances of a resource type, we're going to use something that looks a bit like Banker's algorithm again to be able to detect whether a deadlock has happened. Our data structures are available, allocation, and request. And the detection algorithm is somewhat similar. Set your work equal to available, and if allocation is not equal to 0, then finish is equal to false, otherwise finish is equal to true. And find an index such that both they haven't finished or finish is equal to false, and the work, what you have working, your working number of resources is actually greater than their request. 3 is where we're going to do our addition of the work to the allocation, and 4 we will finish, and if any of the processes finish entry is still false, then it is the system is deadlocked, and it also tells us which processes are actually deadlocked. This algorithm requires an order of m times n squared operations to detect whether the system is in a deadlock state. Okay, so one thing you'll notice that's different here is there is no max allocation graph. So we had the max allocation data set. Before in Bankers, we had the max allocation data set because we wanted to know if the system, if it was possible for resources to be requested in such a way that the system could not fulfill all the requests without getting into a deadlock. Here we don't have to know what's happening in the future because we're trying to detect if we're in a deadlock state right now. Okay, so according to the algorithm, we're going to set all of these, since there's none of the allocations that are 0, because if an allocation is set to 0, we can set its finish entry to true, but they are all false. And I did that again. Okay, so they're all false. And so there is no request here for P0, so P0 can finish, and we can actually add its resources back in. That gives me 1. And also there's no request for P2, so I can add P2's request or resources back in. And so that gives me 3, 1, 3. And now can I fulfill requests? Well, I certainly can fulfill the request for P3, which then would give me 2, 1, 1, and that would be 5, 2, 4. And so far we've done P1, we've done P0, we've done P2, we just did P3, and so now we can do P1, which is requesting that, and that's going to give me 2 back here. And that's 7, 2, 4. And then the last one, of course, is going to be P4, and we can certainly satisfy that request, and we get 2 back. 7, 2, 6, which is the actual number of instances in the system. So this means the system is not deadlocked because you can get true for all I. Okay. Here's another instance. P2 changes its request for an additional type of C, or to an additional instance of C. And so before, now can we tell if the system is deadlocked or not? And of course we'll set all of these to F, and then of course our allocation, which is on a previous page. I'm not going to attempt to try to rewrite that on here, although that probably would be good. So here's the requests. That are outstanding right now, and we have 0, we have 0, 0, 0 outstanding, right? And we can, since P0 still has no request, we can finish that one up and then do 0, 1, 0, right? And that was what its allocation was. And so that gives us 0 A's, 1 B, and 0 C's. Now, can we fill any of these other requests? And in actuality, we cannot. So the system is actually deadlocked. And it looks like the processes, so we got P0, but we didn't get these processes. The deadlock not only exists, but processes 1, 2, 3, and 4 are actually part of that deadlock. So this works quite a bit like bankers, but not exactly. But this allows us to be able to detect when a system has a deadlock and what the processes are, and which processes are actually involved. Of course, now the question is just how practical is it to find or detect deadlocks? You know, how often do you invoke a detection algorithm? Should probably depend upon how likely a deadlock is to occur, and how many processes would be affected or need to be rolled back. If a detection algorithm is invoked arbitrarily, there may be many cycles in the resource graph, and we may not be able to tell very easily the easiest way to fix the deadlock. So there may be lots of resources involved and lots of processes involved, and it just may not be obvious that if I preempt this one process and cancel its allocations, that's necessarily going to fix the deadlock. That piece is a little harder to do. So we talked about recovery. I started alluding to recovery from deadlock. There's a couple options. You can use process termination. You can try to abort all the processes. You can abort them one at a time and in order. You can do priority, who has processed the longest, who has the most left to do. How many resources does the process have? How many resources does the process need to complete? Is the process interactive or batch? All of those are criteria that you can use to determine which process should be terminated. Another possibility is resource preemption. Select a victim, roll it back to some safe state, and then reallocate all of its resources. Of course, if the same process is always the victim, then you may have a process that will starve because it will never be allocated the resources it needs to finish. And so that is the end of Chapter 7. It is important for you to know how to use resource allocation graphs and when. Banker's algorithm, and then also use wait for graphs and the detection algorithm for deadlock detection. You should know about how to prevent deadlocks, some strategies for preventing deadlocks. And of course the other ones are strategies for deadlock avoidance and deadlock detection. Okay, thank you.